Tonight, we're going to follow Voyager 1 from its first mile above Florida to a distance no other human-made object has reached. More than 15 billion miles from Earth, the spacecraft is approaching a simple boundary that makes the separation easier to feel. One light day from Earth. A command sent from home must cross almost an entire day before it arrives. The answer must cross the same darkness back, yet the machine is still listening. By the end of tonight, you're going to understand exactly how Voyager acquired the speed that still carries it outward, how hardware designed in the 1970s survives on a shrinking supply of electricity, and what its two remaining science instruments can measure beyond the sun's protective bubble. The journey is a line through space, but it is also a line through the history of engineering. Every outward mile makes the radio weaker, the reaction slower, and the mission more dependent on choices made before launch. Before we get started, if you love exploring the farthest reaches of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. There is no road beneath Voyager 1. There are no mile markers floating beside it, no destination sign ahead, and no engine burning continuously at the rear. The spacecraft mostly coasts. Gravity gave it a path. Momentum preserves that path. Small thrusters turn its antenna toward Earth, but they do not push it toward another world. Its great distance is the accumulated result of nearly half a century spent moving in one direction. On November 18, 2026, NASA calculates that the Earth Voyager distance will reach 16,094,799,096 miles, the distance light covers in 24 hours. Earth itself moves around the sun, so the number between planet and spacecraft can rise or briefly fall with the seasons. The deeper fact does not change. Voyager is escaping at roughly 3.5 astronomical units per year, hundreds of millions of miles added to the journey during each orbit Earth completes. The title calls it the loneliest machine ever built. Loneliness is not a quantity an instrument can measure. It has no unit, no agreed threshold, and no place in a telemetry packet. But Voyager supplies a physical picture for the word. It is the farthest working artifact of a civilization, separated from its makers by nearly a day at the speed limit of information. Its cameras have been dark since 1990. Most of its instruments are silent. It has no world ahead that it is scheduled to visit. Still, it is not abandoned. 3 radio complexes on Earth take turns following its position. Engineers prepare commands for computers older than many of the people now operating them. A dish 3.7 meters wide holds its narrow beam toward a moving planet that has become a bright point beside the sun. The story begins where that separation was 0. Voyager 1's first mile was vertical. On September 5, 1977, a Titan III center stood at Launch Complex 41 at Cape Canaveral, Florida. The complete rocket was nearly 50 meters tall, while the spacecraft at its top was compact enough to resemble an unusually elaborate small car. Fuel, engines, tanks, structure, and guidance surrounded a machine that would spend only minutes attached to its launch vehicle and then decades traveling alone. At 12:56 when Coordinated Universal Time, the rocket left the pad. The first movement was slow because the launch vehicle begins by lifting almost all of its own propellant. Within seconds, the vehicle climbed through the humid lower atmosphere. Within minutes, stages that had performed their single task were falling away. The spacecraft crossed 1 mile, then 10, then 100. Florida curved beneath it. The name Voyager 1 can make the launch order sound obvious, but Voyager 2 had departed 16 days earlier. The numbering described mission trajectories rather than a simple calendar. Voyager 1 followed a faster route to Jupiter and Saturn, so it would reach both planets first. Voyager 2 took a path that preserved a possible continuation to Uranus and Neptune. One launched first, the other arrived first. Even the names carry the geometry of the mission. If you had stood on the coast and watched the exhaust narrow into the sky, nothing visible would have revealed a future measured in light hours. The rocket did not look different because its payload would still work in 2026. It was one launch among many in an era of large planetary ambitions. The final destination approved for Voyager 1 was Saturn, not interstellar space. The spacecraft had been designed for a 5-year primary mission. Jupiter and Saturn were the assignment. The heliopause was a hoped-for possibility far beyond the official planetary tour, not a milestone the hardware was guaranteed to survive. Many of the engineers who chose its circuits, insulation, backups, and command logic were solving immediate questions: how to withstand launch vibration, and how to cross Jupiter's radiation belts, how to point cameras during a fast flyby, and how to return data from Saturn. Mile Zero therefore contained a quiet asymmetry. The people knew when the machine would leave, but not when it would stop. Spacecraft do not age by calendars alone. They age through radiation, thermal cycling, lubricant behavior, propellant chemistry, switching operations, and the slow decline of power. A 5-year design can fail in one day if a critical part breaks. It can also keep operating when conservative margins, redundant paths, and careful control stretch far beyond the original plan. Below Voyager, the launch pad became a small mark. Ahead of it lay Jupiter, more than 400 million miles from the Sun at average distance. Yet Jupiter was not the first cause of the journey. The route had begun with 4 planets lining up in a way that made a particular chain of gravity assists possible. The outer planets do not form a straight line. Jupiter completes an orbit in less than 12 Earth years. Saturn takes about 29.5. Uranus needs 84, and Neptune about 165. Their changing positions occasionally create a broad geometric arrangement in which a spacecraft can pass one planet and be redirected toward the next. The useful Voyager arrangement occurs roughly once every 175 years. This was not a single night when 4 planets stood neatly together. It was a launch window spread across the late 1970s, defined by trajectories that could connect encounters over the following decade. Engineers studied more than 10,000 possible paths before selecting the 2 Voyager routes. Each candidate had to satisfy planetary arrival dates, flyby distances, illumination, instrument pointing, radio visibility, and the amount of course correction the spacecraft could perform. Gravity assist sounds like a planet donating speed. The fuller description depends on the reference frame. Relative to the planet, the spacecraft falls inward, accelerates, bends around the world, and climbs away with nearly the same speed it had on arrival. Relative to the Sun, the moving planet changes the spacecraft's direction and transfers a tiny amount of orbital energy. The planet slows by an immeasurably small fraction. The spacecraft can leave moving faster with respect to the Sun. Imagine that you roll a small ball toward a much larger moving platform. If the encounter is arranged correctly, the platform changes the ball's direction while carrying it forward. The platform barely notices. Jupiter is the platform on a planetary scale, moving around the Sun at roughly 8 miles per second and possessing enough gravity to bend a spacecraft's route over hundreds of thousands of miles. Without gravity assists, a spacecraft would need much more launch energy or far more travel time to reach the outer planets. NASA's Voyager fact sheet notes that the technique reduced a possible Earth to Neptune journey from about 30 years to 12. For Voyager 1, the chain had a different final purpose. Jupiter would send it towards Saturn. Saturn and Titan would then choose the angle at which it left the plane of the planets. If you draw the path on a sheet of paper, The line looks smooth. The real route was a sequence of moving targets. Launch a little too early, and Jupiter would not occupy the required point. Pass Jupiter at the wrong altitude, and Saturn would be missed years later. Aim for Saturn in the wrong way, and Titan would not fall inside the observation geometry. Every later mile depended on an earlier mile being crossed at the right moment. The rare alignment supplied an opportunity, not a vehicle. A spacecraft still had to survive the distance, navigate with limited propellant, and carry instruments capable of returning useful measurements. The machines approved for that task were identical twins, built around a large white dish and a 10-sided metal body. The twins also protected the science from one imperfect outcome. Both would visit Jupiter and Saturn on different paths and dates. Their overlapping observations could confirm changes in clouds, rings, fields, and moons, while their diverging routes extended the possible return. Voyager 1 favored Titan and a fast northern departure. Voyager 2 preserved the chain to Uranus and Neptune. Mission design did not place every ambition into one vehicle. It distributed ambition across two machines whose similarities made comparison possible and whose differences made the full tour possible. That distribution became a form of insurance without reducing either spacecraft to a spare. A failure on one would not erase every outer planet objective. Success on both would create a paired record separated in time. At Saturn, 9 months between encounters allowed features to be revisited. Across the later Interstellar mission, 2 directions through the heliosphere revealed that its boundary does not sit at one universal radius. The geometry chosen before launch continued producing comparative science decades after the Grand Tour window had closed. Voyager 1 weighed about 815 kilograms at launch, including its hydrazine propellant. That is roughly 1,797 pounds, close to the mass of a subcompact car. The comparison ends with weight. A car keeps most of its parts inside a compact shell. Voyager unfolds booms and antennas until its working shape spans far beyond its central body. The most visible feature is the high-gain antenna, a white parabolic dish 3.7 meters across. The dish is not a decoration or a passive shield. It is the narrow doorway through which nearly every command and measurement must pass. When Voyager points correctly, the antenna focuses radio energy toward Earth and gathers the weak commands arriving from Earth. If pointing drifts too far, the distance can become functionally absolute, even while the spacecraft remains healthy. Beneath the dish sits the bus, a 10-sided electronics housing about 1.8 meters in diameter. Separate bays hold transmitters and other assemblies. 3 computer systems divide responsibilities. One interprets commands and manages fault protection. One controls attitude and moving parts, and one packages science and engineering data. They do not resemble a modern laptop concentrated on one board. They are distributed, redundant machines built from 1970s electronics. A 13-meter magnetometer boom carries magnetic sensors away from electrical interference generated by Voyager itself. 2 10-meter antennas form a broad 5 for the plasma wave and planetary radio experiments. A separate boom holds 3 radioisotope thermoelectric generators. Another supports instruments once aimed at planets from a movable scan platform. If you saw the probe as a silhouette, it would look less like a sealed vehicle than an arrangement of balances. The long booms separate sensitive detectors from noise. The RTGs are kept away from instruments. The dish defines one axis, pointing toward Earth. Small thrusters rotate the whole assembly around that axis, or nudge it across the sky. If you floated beside Voyager during cruise, the dish would be wider than your outstretched arms, and the magnetometer boom would extend about the length of a city bus. Yet the central electronics would fit within a modest room. The architecture turns separation into function. Distance between components improves what they can measure. The original science payload supported 10 instruments and an 11th investigation using the radio system. Cameras, ultraviolet and infrared instruments, particle detectors, plasma instruments, a magnetometer, and radio receivers gave the spacecraft several ways to read an environment during a brief flyby. It could see clouds and moons, listen to plasma, measure fields, count particles, and use its own radio signal to probe atmospheres and rings. Most of that payload is now off. The shape remains. The dark cameras still occupy the scan platform. The booms are still extended. The dish still points home. Voyager carries its entire earlier mission outward, including every component no longer drawing power. But before any instrument could work at Jupiter, the spacecraft needed to convert launch speed into a carefully timed encounter. Voyager 1 did not fly toward Jupiter in a straight line drawn across a fixed solar system. Earth, Jupiter, and the spacecraft all moved around the Sun. Mission navigation predicted where Jupiter would be in March 1979 and aimed toward that future location. The path curved continuously under solar gravity, while small course corrections refined the arrival. The Titan Centaur gave Voyager enough energy to begin an outer planet trajectory. After separation, the spacecraft deployed its booms, established communication, and started the long process of checking systems. A launch is violent. Deep space cruise is quiet, but the transition between them asks many mechanisms to work once and work correctly. A boom that failed to deploy would contaminate magnetometer measurements. A dish that could not point would end the conversation. A stuck scan platform would reduce the planetary encounter before it began. The initial months also demonstrated a principle that would define the mission. Voyager could be reprogrammed across space. Engineers did not need every operation to be fixed permanently before launch. They could transmit sequences, change how hardware was used, and adapt observations to discoveries. The communication delay was still measured in minutes during the early cruise, but every instruction already required careful modeling. The spacecraft could not be steered like a remote-controlled car with immediate visual feedback. At the beginning, 1 light hour was a distant threshold. Earth itself lies about 8 light minutes from the Sun. Jupiter's varying distance from Earth produces a radio delay of tens of minutes. That was manageable compared with Voyager's present delay, yet it already separated action from confirmation. Engineers would send a command, wait for it to reach the spacecraft, then wait again for telemetry to return. You could make several ordinary decisions during that pause. Voyager had to execute the sequence already stored on board. Cruise time became preparation time. Instruments were calibrated. Navigation images located stars and planets. Engineers measured the spacecraft's radio signal to refine its trajectory. Jupiter grew from a bright point into a disk. Its 4 large Galilean moons began to separate in the cameras. The system that had been studied for centuries through telescopes was becoming a place with depth. Voyager 1 was the faster twin because its route was shorter and more energetic. It caught and passed Voyager 2 on the way outward, reaching Jupiter on March 5, 1979. The label 1 had become true in arrival order. Speed alone was not the purpose. A fast flyby limits observation time. The spacecraft had to rotate its scan platform, change filters, record data, and transmit what it could while moving through a radiation environment far harsher than the one near Earth. The encounter was a compressed campaign. Months of planning would unfold over days, with the closest pass measured in hours. Ahead lay a planet so large that every other planet in the solar system could fit inside it by volume, and a magnetic domain extending millions of miles into space. Jupiter began influencing Voyager long before the closest approach. Gravity is not a gate crossed at a specific mile. It strengthens continuously as distance closes. The spacecraft accelerated while the planet's disk expanded in its cameras. Moons traced changing positions. The magnetic field and charged particle environment announced the giant planet beyond the visible clouds. Mission planners had selected the flyby to gather science and set up Saturn. Those goals were inseparable. The altitude and direction that improved one observation could alter the later trajectory. Navigation therefore worked backward from future requirements. Saturn's position in 1980 constrained the way Voyager approached Jupiter in 1979. Titan's desired encounter constrained the way it would later pass Saturn. The spacecraft met Jupiter's bow shock, where the solar wind encounters the planet's magnetic obstacle. Beyond it lay the magnetosphere, an enormous region controlled by Jupiter's field and filled with charged particles. Jupiter rotates in just under 10 hours, sweeping its magnetic environment around with it. Io supplies sulfur and oxygen from volcanic material, helping form a torus of plasma around the moon's orbit. Radiation presented a serious engineering test. Energetic particles can flip electronic states, create noise in images, and damage components. Voyager carried shielding and fault protection, but it could not hide inside a thick vault. Mass was limited. The encounter required hardware to continue operating while immersed in a region that would be lethal to an unprotected human traveler. If you approached along Voyager's path, Jupiter would stop looking like a striped sphere on a black field. The planet would fill more of the view each day. The great red spot would reveal swirls within swirls. Small shadows would cross cloud tops. The moons would become separate worlds rather than points of light. On March 5, 1979, Voyager 1 made its closest approach, passing about 172,000 miles above the cloud tops by the mission fact sheet's measure. That distance is comparable to much of the Earth-Moon gap, yet it was close enough for a transformation in planetary science. The images resolved atmospheric currents and moon surfaces. The fields and particles instruments sampled a magnetic system on a scale unavailable from Earth. The flyby also gave Voyager energy with respect to the Sun. Jupiter's moving gravity bent the trajectory and raised the heliocentric speed, aiming the craft onward to Saturn. There was no long engine burn announcing the change. The planet performed the turn. Every mile afterward carried evidence of that encounter in the direction and velocity of the spacecraft. Even now, beyond the heliopause, Voyager's path is partly a fossil of a few days near Jupiter. The most consequential surprise did not come from the planet's clouds. It came from a moon whose surface should have appeared old and cratered, but instead looked violently young. Io is roughly the size of Earth's moon, but the resemblance ends at scale. Before Voyager, scientists knew that Jupiter's gravity and orbital resonances affected the moon. The extent of the resulting activity was not yet visible. Voyager 1 changed that picture in March 1979. Images showed a surface colored by sulfur compounds, with broad plains, pits, and features unlike the cratered landscapes familiar from the Moon, Mars, and Mercury. The shortage of impact craters implied that the surface was being renewed. Then a navigation engineer, Linda Morabito, noticed a plume rising above Io's limb in an image taken after closest approach. The plume was the signature of an active eruption. This was the first active volcanism observed beyond Earth. Later analysis and Voyager 2 observations confirmed multiple active centers. Plumes could rise hundreds of kilometers. Material left the moon and entered Jupiter's magnetic environment, linking geology on a small satellite to plasma surrounding the largest planet. The energy source is tidal flexing. Io orbits deep within Jupiter's gravity, while Europa and Ganymede tug with a repeated rhythm. Its orbit remains slightly non-circular. As Io moves closer to and farther from Jupiter, the strength and direction of tidal forces change. The solid moon flexes. Internal friction converts that deformation into heat. You can bend a wire repeatedly and feel it warm near the fold. Io is not a wire, and its heating involves an entire world's interior, but the analogy captures the conversion. Repeated distortion becomes heat. On Io, the process melts rock and drives persistent volcanism. The discovery changed more than one moon. It proved that a small world far from the sun could remain geologically active through orbital energy rather than sunlight or long-retained formation heat alone. That principle now shapes the study of icy moons, subsurface oceans, and potentially habitable environments elsewhere in the outer solar system. Voyager's cameras had been built to survey worlds. At Io, they revealed a process. A single plume above a curved horizon connected orbital mechanics, interior heating, surface renewal, and Jupiter's magnetosphere. The encounter became a reminder that the solar system was not a museum of finished objects. The machine continued moving. It could not orbit Io, return for a second close pass, or wait for another eruption. A flyby preserves no opportunity except the one planned. Data had to be recorded, transmitted, interpreted, and handed to future missions. Galileo and Juno would later study the Jovian system in greater detail, but Voyager had supplied the first unmistakable view of the active moon. As Jupiter fell behind, the outward trajectory gained another meaning. Voyager 1 was leaving a solar system that had just become more dynamic than scientists had expected. Io was the brightest surprise, but not the only one. Voyager 1 found that Jupiter possesses a faint ring, a dark and delicate structure difficult to see from Earth. Saturn was no longer the only giant planet with rings. Later observations would show that all 4 giant planets have ring systems, each with its own materials and dynamics. Jupiter's ring is made largely of small dark particles. Backlighting helps reveal it because the grains scatter sunlight toward the camera. The structure lies close to the planet and is continually affected by small moons, impacts, radiation, and magnetic forces. Later Galileo data connected much of the dust to debris knocked from inner moons by meteoroid impacts. The ring is not a miniature version of Saturn's bright icy bands. It is a separate kind of system. Europa offered a different puzzle. Voyager images showed a bright surface crossed by long dark lines and relatively few large craters. At the available resolution, some features seemed almost drawn across the ice. The visual evidence suggested a young, mobile crust. Later missions would strengthen the case for a global saltwater ocean beneath the frozen exterior, but Voyager supplied the first broad map of a surface that did not resemble an ordinary dead satellite. Ganymede revealed grooved terrain beside older dark regions. Callisto displayed an ancient, heavily cratered face. 4 large moons in one system represented 4 geological histories. Jupiter itself contained long-lived storms, fast jet streams, auroras, and cloud layers organized by rotation. The magnetometer and particle instruments connected those visible worlds to an invisible environment far larger than the planet. If you could trace the Jovian magnetosphere at human scale, it would resemble an enormous windsock, compressed toward the sun and stretched far behind Jupiter. Charged particles spiral around magnetic field lines. Io's material joins that flow. Radio emissions and energetic particles make the system detectable in ways that have no direct visual equivalent. Voyager's instruments divided the work. Cameras recorded reflected light. The magnetometer measured field direction and strength. Particle detectors counted incoming energies and species. Radio and plasma wave instruments listened across selected frequencies. No single detector contained the whole encounter. The scientific portrait emerged by aligning measurements in time and location. That method would become even more important after the cameras went dark. In interstellar space, Voyager would know its surroundings through fields and particles alone. The Jupiter flyby was therefore both an imaging triumph and a rehearsal for invisible science. The planet had also completed its mechanical role. Its gravity redirected the spacecraft toward Saturn and increased the speed that still carries Voyager outward. A curve lasting days became a consequence lasting millennia. Jupiter receded into a bright star. The next major encounter lay more than a year ahead, around a world whose rings could be seen from Earth but had never been examined at Voyager's range. Saturn would provide the mission's second planetary destination and Voyager 1's final turn. Jupiter's visible disk ends at its cloud tops. Its magnetic presence continues for millions of miles. Voyager 1 crossed that extended domain on the way in and again on the way out, recording boundaries that shifted as the solar wind pressed against them. The planet was surrounded by a changing environment rather than a rigid shell. The magnetosphere matters because charged particles do not travel through it as neutral dust would. Magnetic and electric fields guide them, accelerate them, and direct some into planetary atmospheres. Jupiter's fast rotation sweeps the field around. Io adds fresh material. The result is a coupled machine with a rocky moon functioning as both a volcanic source and an electrical conductor. Across Io, motion through Jupiter's field creates a voltage of roughly 400,000 volts. Currents flow along magnetic field lines between moon and planet. Ultraviolet emissions mark the connection in Jupiter's upper atmosphere. The little world and the giant are separated by hundreds of thousands of miles, yet joined electromagnetically. Voyager's magnetometer measured the field without taking a picture of it. The long boom placed the sensors away from currents and magnets aboard the spacecraft. Engineers could subtract remaining spacecraft effects and map the larger environment through changes in direction and strength. Particle instruments added energy and composition. Radio observations revealed emissions associated with the rotating system. If you could see every measured field line, Jupiter would appear nested inside a structure larger than the visible planet by orders of magnitude. The moons would orbit within it. The ring would sit inside it. Io's sulfur and oxygen would trace a torus around it. The familiar striped sphere would become only the dense center of a dispersed electrical landscape. The encounter also demonstrated why a spacecraft carries instruments with overlapping goals. A single detector can fail or provide an ambiguous signal. Several independent measurements can establish a stronger interpretation. Decades later, Voyager's heliopause crossing would require the same logic. Magnetic fields, cosmic rays, low-energy particles, and plasma waves would change in related ways, though not always in the way models predicted. The distance from Jupiter increased at thousands of miles per hour. Its magnetotail extended behind the planet, but eventually Voyager returned to the solar wind. Data continued downlinking after the best images had been taken. The spacecraft's digital tape recorder could preserve selected high-rate observations for later playback, a necessity when the instruments gathered information faster than the radio could return it. Every planetary flyby contains this imbalance. The event happens once. Transmission can take weeks or months. When you receive the record on Earth, you reconstruct a world after the spacecraft has already moved on. Voyager 1 was now committed to Saturn. The gravity assist had worked. The next million miles were no longer a guess about direction, but a narrowing corridor toward another moving planet. Jupiter gave Voyager 1 much of the outward speed that defines the mission today. The spacecraft left the encounter traveling toward Saturn on a solar escape path that later gravity would refine. Its speed with respect to the Sun settled near 17 kilometers per second, roughly 39,000 miles per hour, though the exact value depends on date and reference frame. At 39,000 miles per hour, a machine crosses 1 million miles in a little more than a day. It crosses the average Earth-Moon distance in about 6 hours. It can travel the circumference of Earth in well under an hour. Those comparisons make the motion sound swift. Interstellar scale makes it small again. Even after nearly half a century at that pace, Voyager is only approaching 1 light day from Earth. Light covers in 24 hours what the spacecraft needed from 1977 to late 2026 to place between itself and a moving Earth. The ratio is severe. Voyager moves at about 1/18,000th of light speed. If you watch the spacecraft cross a scale model where light moved 1 foot per second, Voyager would creep less than the thickness of a sheet of paper during that second. Human engineering made it the fastest outward moving of the 2 Voyagers. Physics keeps it profoundly slow beside light. This contrast explains the radio delay, but also the endurance of the mission. Voyager is not racing through a crowded environment. Beyond the planets, matter is sparse. There is no atmospheric drag to bring it to a stop, and no road friction consuming its momentum. The spacecraft will continue along a gravitational trajectory, even after its power disappears. The small hydrazine thrusters are not the source of its long-distance speed. They orient the spacecraft and once performed modest trajectory corrections. The launch vehicle, Jupiter and Saturn, supplied the main energy changes. This distinction matters when engineers discuss remaining propellant. Running out of attitude control capability would end communication, but it would not cause Voyager to halt. Silence and motion are separate outcomes. Distance accumulated steadily during the cruise to Saturn. The radio delay grew. Sunlight weakened by the inverse square law. At twice the distance, illumination falls to 1/4. Near Saturn, sunlight is roughly 1% as intense as at Earth. Solar panels sized for the inner solar system would have become impractical, which is why Voyager carried nuclear power from the beginning. Jupiter had converted a flyby into a permanent change of orbit. The result can be measured in every outward mile, yet no fuel tank aboard Voyager paid the main cost. A planet lost a fraction of motion too small to notice. A spacecraft gained enough to cross the heliopause and continue toward the stars. The next planet would alter direction more dramatically than speed. Saturn waited with a moon wrapped in orange haze. Saturn approached slowly in the cameras and quickly in the mission schedule. From Earth, its rings appear as a clean, bright system divided into a few broad bands. Voyager resolved those bands into a hierarchy of ringlets, gaps, waves, sharp edges, and changing brightness. The familiar ornament became a dynamical disk. Voyager 1 reached its closest approach on November 12, 1980. The spacecraft passed roughly 78,000 miles from Saturn's center by NASA's mission account, close enough to gather detailed images while following a route arranged around Titan. The flyby sequence coordinated cameras, spectrometers, fields instruments, radio science, and precise spacecraft pointing. Saturn's atmosphere appeared quieter than Jupiter's at first glance. A high haze softened contrasts. Beneath it, winds and bands moved around a planet completing a rotation in roughly 10.5 hours. The equatorial winds were among the fastest then measured in the solar system. Magnetic observations found an unusual field aligned closely with a rotation axis. The rings dominated the visual encounter because distance dissolved apparent simplicity. What looks continuous from far away is made of orbiting particles. Collisions, self-gravity, resonances, and the tugs of moons organize those particles. Some structures travel like waves through a disk. Others mark locations where a moon's orbital period relates to the period of ring particles by a simple ratio. If you descended toward the rings, you would not land on a solid platform. The material is overwhelmingly water ice, ranging from grains to much larger pieces, distributed across an immense area with comparatively little total thickness. Empty intervals separate particles even where the rings look opaque from a distance. The brightness comes from countless surfaces reflecting sunlight, not from one sheet. Voyager crossed the system too quickly to follow every change over years, but two encounters 9 months apart allowed comparison between Voyager 1 and Voyager 2. Earth-based observations and later Cassini measurements would extend the timeline. Planetary science advances by combining brief close passes with long remote records. The spacecraft radio also became an instrument. By transmitting through Saturn's rings toward Earth, Voyager allowed scientists to study how the signal was blocked or scattered at different wavelengths. The method revealed particle distributions and ring opacity without relying only on images. A narrow radio beam turned the rings into a measurement screen. Saturn's cloud tops were one milestone. The ring plane was another. Titan was the decisive one. Voyager 1 had been aimed to pass the moon closely because its thick atmosphere represented one of the most compelling questions in the outer solar system. That choice would provide science and close a door. The phrase Saturn's rings hides their number. Broad labels such as A, B, and C remain useful, but high-resolution observations reveal thousands of ringlets and embedded structures. Voyager found narrow components, braided appearances, eccentric edges, and spoke-like markings across the broad B ring. Spokes were especially curious because they did not behave like ordinary material, simply orbiting under gravity. Dark radial markings appeared and changed over relatively short times. Their behavior suggested that tiny charged grains were being lifted or rearranged by electromagnetic effects. Gravity organizes the main architecture, but electrical forces can influence the smallest particles. Small moons help maintain sharp boundaries. A shepherd moon, orbiting near a ring edge, exchanges angular momentum with nearby particles, confining some paths and disturbing others. Prometheus and Pandora flank Saturn's narrow F ring. Their repeated tugs create streamers, clumps, and changing shapes. The ring is not passively contained. It is continually worked. Resonances reach across larger distances. Mimas orbits well beyond the main rings, yet a repeating gravitational relationship helps clear the Cassini division. Other moons launch spiral density waves. In those waves, particles crowd and spread in a pattern that travels through the ring even though individual pieces remain on their own orbits. You can create a loose analogy by watching traffic compress and expand on a highway. The wave of slowing cars can move backward while every car continues forward. Ring density waves are governed by orbital mechanics rather than drivers, but the separation between particle motion and pattern motion is similar. Voyager also expanded the known family of Saturnian moons. Some discoveries were small bodies near the rings, difficult to detect from Earth. Images of larger moons showed water ice surfaces shaped by impacts and fractures. Mimas carried a crater so large relative to the moon that the collision approached the scale of disruption. Enceladus appeared unusually bright and showed signs of resurfacing, decades before Cassini connected its south polar plumes to a global ocean. The rings and moons form one system. Impacts supply debris. Moons create gaps and waves. Ring material can fall into Saturn's atmosphere. Dust can move outward. The boundaries between moon, ring, and planet are active exchanges rather than permanent categories. Voyager 1's images arrived as a sequence of close looks from changing angles. Scientists assembled mosaics, compared filters, and matched visible features to radio and particle measurements. The completed picture contained more order and more irregularity than the telescopic view had suggested. Yet the mission had not been designed merely to count ringlets. One large moon possessed an atmosphere denser at the surface than Earth's. Its haze concealed the ground completely. Passing it closely would reveal composition and pressure while using its gravity to bend Voyager away from every remaining planet. Titan was known to have an atmosphere before Voyager arrived, but its depth and composition made it a priority. The moon is larger than Mercury and wrapped in a photochemical haze. Visible light cameras cannot look through that orange veil to the surface. The atmosphere itself therefore became the main target of Voyager 1's close encounter. Measurements showed a nitrogen-rich atmosphere containing methane and more complex carbon compounds. Pressure at the surface was inferred to be about 1.5 times Earth's sea level pressure. The temperature was near 94 kelvins, about minus 290 degrees Fahrenheit. Sunlight acting on methane high above the surface builds hydrocarbons and haze particles that settle downward. Voyager could not confirm the lakes and seas later mapped by Cassini and Huygens, but it established Titan as a world where organic chemistry occurs on a planetary scale. Methane plays some of the role that water plays on Earth, moving among atmosphere, clouds, rain, channels, and surface reservoirs under far colder conditions. If you had looked from Voyager's camera, Titan would have offered almost no surface landmarks. It appeared as a softly banded orange globe. The absence of visible terrain was itself a measurement. Haze layers extended high above the moon, and radio science could probe the atmosphere as Voyager's signal passed through it. The close flyby demanded a particular trajectory. Voyager approached Titan in a way that allowed the moon's gravity, combined with Saturn's, to bend the spacecraft northward out of the ecliptic plane. The ecliptic is the broad plane in which most planets orbit. Once Voyager left it at a steep angle, Uranus and Neptune were no longer reachable. This was the Titan bargain. A close study of the moon came at the cost of any later planetary encounter for Voyager 1. The mission accepted that exchange deliberately. Voyager 2 preserved the route onward, providing redundancy at Jupiter and Saturn while keeping the Grand Tour option alive. The choice illustrates how exploration turns priorities into trajectories. A spacecraft cannot visit every worthy target. The laws of motion make some observations mutually exclusive. Passing on one side of a moon can open a route. Passing on the other can close it. Science goals become angles measured to fractions of a degree. Voyager 1 left Titan with data about a complex atmosphere and a path pointing away from the planetary disk. There was no engine burn later that could undo the geometry. The spacecraft's planetary career ended because the encounter succeeded exactly as planned. Saturn grew smaller behind it. Uranus and Neptune remained ahead in distance, but far to the side in trajectory. Voyager 2 would eventually visit both. Voyager 1 began a different mission without another world waiting at the end. The loneliest part of the journey started not at the heliopause, but at Titan, when the route stopped connecting named planets. After Saturn, Voyager 1 traveled north of the ecliptic at roughly 35 degrees. The sun still dominated its motion, and the known planets still orbited behind it, but the spacecraft no longer followed the shared disk. Each outward mile increased both radial distance and vertical separation from the planetary plane. Mission operations changed with the geography. Flybies require intense observation sequences and rapid changes in pointing. Interplanetary cruise favors repetitive measurements, periodic calibration, and long spans of steady antenna orientation. Cameras had fewer useful targets. Fields and particles instruments became more important because the outer heliosphere itself was the next environment to explore. The phrase "no next planet" does not mean there was nothing to study. The solar wind changes with distance. Cosmic rays enter from the galaxy. Magnetic fields are carried outward from the rotating sun. Shocks and pressure fronts move through the heliosphere. Voyager could sample processes that no telescope near Earth could measure locally. But the emotional geometry changed. At Jupiter and Saturn, the machine approached bright destinations. After Saturn, every major object was behind it. The path did not intersect Pluto, another planet, or a planned asteroid. The next named boundary, the termination shock, had an uncertain location. The heliopause was farther and still less certain. If you placed yourself beside the spacecraft, the sun would remain the brightest star, but it would no longer present a disk to unaided vision. Earth would be inseparable from the solar glare. Radio navigation could describe home precisely while ordinary sight could not. Voyager did not need to know where Earth looked by recognizing the planet itself. Stored pointing information, celestial references, gyroscopes, star sensors, and ground commands kept the high-gain antenna aligned. The spacecraft's relationship to Earth became mathematical. Angles, predicted motion, signal strength, and timing. The mission was renamed and extended. On January 1st, 1990, the Voyager Interstellar mission formally began. The new objective was to explore the outer limits of the sun's influence and, if the hardware lasted, the region beyond. A vehicle designed to pass planets had become a moving observatory for a boundary no one had crossed. That transformation required subtraction. Systems useful at Jupiter could be turned off to preserve power. Heaters could be reduced. Observation schedules could become simpler. A machine survives a long mission partly by carrying capability and partly by learning which capability to surrender. The route had become almost entirely coast. Momentum did the traveling. Electricity did the measuring, thinking, warming, and talking. As sunlight faded, the source of that electricity sat on a boom behind the central bus, converting the decay of plutonium-238 into a few hundred watts. Voyager 1 could never have depended on solar panels. At Jupiter, sunlight is about 1/27th as intense as at Earth. Near Saturn, it is roughly 1/90th. Beyond the heliopause, a practical 1970s solar array would have been enormous and ineffective. The spacecraft instead carries 3 multi-hundred-watt radioisotope thermoelectric generators, or RTGs. Each generator contains plutonium-238 dioxide. Radioactive decay releases alpha particles and heat. Thermoelectric materials convert a fraction of the temperature difference between the hot interior and cold space directly into electricity. There is no turbine, piston, or rotating generator. The decay is steady, and the conversion has no major moving part. At launch, each Voyager RTG produced about 158 electrical watts, for a total near 470 watts. That was modest even in 1977. It would not power a modern kitchen full of appliances, but a spacecraft designed around efficiency could operate computers, radio, instruments, heaters, and controls within that budget. Plutonium-238 has a half-life of about 87.7 years. Its thermal output declines gradually, and the thermoelectric materials also age. NASA describes the Voyagers as losing roughly 4 watts of available electrical power each year. By 2023, the total was reported near 225 watts. The decline continues. If you remove 4 watts from a household, the change is trivial. Remove 4 watts from a machine already operating close to its minimum, and a decision becomes necessary. A heater, instrument, or backup function must eventually go dark. The Voyager team maintains a ledger in which every fraction of power matters. Heat creates a second balance. The spacecraft needs electricity, but it also needs components to remain warm enough. Turning off a heater saves power while exposing fuel lines, electronics, and instruments to lower temperatures than their original test limits. Some instruments have continued working far below those limits, revealing engineering margin that could not be guaranteed in advance. The RTGs also warm the spacecraft indirectly, yet deep space remains cold and the vehicle radiates heat continuously. Insulation slows the loss. Electrical heaters protect selected parts. Mission managers choose which temperatures to accept and which systems deserve the remaining energy. This is why instrument shutdowns do not represent sudden mission failure. They are deliberate exchanges of capability for time. In February 2025, Voyager 1's cosmic ray subsystem was turned off. In April 2026, the low-energy charged particle experiment followed. The saved power supports the remaining spacecraft and its 2 active science instruments. Every outward mile is therefore paid for twice. Momentum pays the mechanical cost of motion without additional fuel. Radioactive decay pays the electrical cost of keeping that motion scientifically connected to Earth. One resource is effectively abundant. The other shrinks by about 4 watts each year. The power system can remain smooth while another limit arrives first. A computer memory chip can fail. A thruster line can clog. An antenna can lose its aim. Longevity depends on systems that were built with backups and on people who can still reason through them across an almost 2-day conversation. Voyager's computers are not one general-purpose machine. The command computer subsystem manages commands, stored sequences, fault detection, and corrective routines. The attitude and articulation control subsystem maintains orientation and controls pointing. The flight data subsystem gathers, formats, and prepares engineering and science information for transmission. Together, they execute on the order of 8,000 instructions per second. A modern smartphone performs billions of operations in the same interval. The comparison is useful only if it does not become contempt. Voyager's computers were designed for deterministic work, radiation tolerance, and an environment where no technician could replace a board. They have operated continuously for nearly half a century. Memory is measured in thousands of words rather than gigabytes. The command computers have roughly 1,518-bit words available for sequence instructions and antenna pointing information. Engineers make that small space useful by repeating activities. A compact baseline sequence can cycle an observation or calibration without storing every instance separately. If you wrote a set of instructions on a small card, repetition would save room. Measure once every hour occupies less space than listing every hour for a year. Voyager uses the same principle in a rigorous machine language, turning limited memory into long autonomous schedules. Autonomy is essential because ground control is always late. A fault cannot wait nearly a day for an engineer to see it, another day for a command to arrive, and another day for confirmation. Fixed routines detect selected problems and place the spacecraft in safer configurations. The machine must protect itself with the knowledge stored on board. the limits also encourage care. Commanding Voyager is not a process of sending a large software update and hoping to revise it later. Engineers inspect memory maps, timing, power state, thermal consequences, and interactions among subsystems. A change that appears small on Earth can alter a unique machine 15 billion miles away. The computers have been reprogrammed repeatedly. New sequences extended the mission. Ground teams worked around failed hardware. Capabilities changed as instruments were switched off. The code now operating is a layered history of original design and later adaptation. That history became visible during the data crisis that began in November 2023. The spacecraft still received commands and continued operating, but returned unreadable science and engineering information. The failure was eventually traced to a memory chip in the flight data subsystem. Repairing it required relocating code into spaces that had not been intended to hold it. The crisis would be solved through the same quality that sustained the mission, limited resources understood precisely. There was no spare modern computer aboard. There was a map of old memory, a radio link, and a team willing to divide one block of code into pieces. Before reaching that chapter, the signal itself must be followed from Voyager's dish to Earth. The 3.7-meter high-gain antenna defines Voyager's posture. Its center line points toward Earth. The spacecraft can roll around that line while keeping communication, but larger pointing errors reduce the signal quickly. Thrusters provide small corrections as the target direction changes. Earth is not fixed. It orbits the sun, rotates daily, and carries the receiving antennas with it. Voyager also moves. Navigation predicts the line between them and accounts for the time radio waves spend in flight. A command is aimed not only toward where the spacecraft appears, but toward where it will receive the signal after many hours. The Deep Space Network maintains 3 principal complexes spaced around Earth: Goldstone in California, Madrid in Spain, and Canberra in Australia. As the planet rotates, one complex can hand a distant spacecraft to another. Large dishes collect signals too weak for ordinary receivers and transmit focus commands with enough power to be detected far away. The 70-meter DSS-43 antenna near Canberra has played a special role for Voyager. During a 2025 maintenance period, NASA described it as the only dish with enough signal power to send commands to the Voyagers, though other network assets could still receive under appropriate conditions. The dependence shows how the link includes infrastructure on both ends. If you stood beneath a 70-meter dish, its bowl would span most of a city block. Voyager's own dish is about the width of a small room. The two instruments face each other across billions of miles with no physical guide between them. Uplink commands travel at only 16 bits per second. Normal X-band telemetry can return around 160 bits per second, with higher rates available for selected plasma wave playback. These numbers are tiny beside terrestrial networks. They are adequate because Voyager does not send video now. It returns compact measurements, engineering states, timing, and the organized results of instruments that sample slowly. Bandwidth shapes thought. A photograph contains many pixels. A magnetic field reading can be represented by a few numbers and a timestamp. A diagnostic memory dump must be scheduled and transmitted over hours. Engineers choose what to request because link time is limited, and every bit crosses almost a day of space. The radio path is also a measurement tool. Doppler shifts reveal line-of-sight velocity. Signal timing refines distance. During planetary encounters, changes as the signal passed through an atmosphere or ring helped reveal density and structure. Communication and science occupy the same wave. Voyager's dish cannot feel loneliness. It performs geometry. Yet its unwavering orientation supplies the mission's clearest image of connection. The spacecraft is traveling away from every planet it visited, but one face remains turned toward Earth. Its body moves outward. Its antenna looks back. Receiving the signal requires time as well as area. The Deep Space Network does not point at Voyager once and leave every dish there permanently. Antenna hours are shared among many missions. Schedules account for planetary visibility, spacecraft needs, maintenance, and which complex can see the target above its local horizon. A Voyager pass may last for hours while the faint carrier is acquired, tracked, and decoded. Several antennas can sometimes be combined to improve sensitivity, effectively creating a larger receiving aperture through coordinated electronics. Navigation is extracted from the same contact. The carrier's Doppler shift measures motion along the line of sight. Ranging tones help determine distance. Very small errors in trajectory accumulate across years, so repeated radio observations refine the prediction of where the dish must point next. The link tells Earth where Voyager is while telling Voyager where Earth will be. Communication, navigation, and science share one narrow beam and one limited schedule. Voyager's radio transmitter operates at roughly 23 watts. A small household light can use comparable power. Near the spacecraft, the focused transmission is strong enough to carry information. By the time it spreads across billions of miles, the part intercepted by an antenna on Earth is extraordinarily weak. Radio intensity falls as the signal expands. Double the distance and the same energy is distributed across 4 times the area. Multiply the distance by thousands, and the receiving problem becomes one of extracting a known pattern from thermal noise, natural radio sources, and interference created on Earth. The Deep Space Network succeeds by combining several advantages. Its dishes provide large collecting areas. Cryogenically cooled electronics reduce receiver noise. Precise frequency prediction tells operators where to listen. Coding allows some corrupted bits to be detected and corrected. Long integration can accumulate evidence for a signal too faint to recognize instantly. If you looked at Voyager in an optical telescope, you would not see the spacecraft itself. Its reflected sunlight is too faint and its angular size too small. Radio provides a different kind of visibility. Very long baseline array antennas once combined observations to locate Voyager as a tiny radio point against distant sources. The image was not a detailed portrait. It was proof of position through transmission. Each downlinked bit represents a decision made onboard. A magnetometer reading becomes a number. A plasma wave measurement becomes a frequency and amplitude. Temperatures, voltages, switch states, and error counters become engineering telemetry. The flight data subsystem arranges them into frames. The transmitter modulates them onto an X-band carrier near 8.4 gigahertz. The return path is one way in more than a geometric sense. A bit that fails to arrive cannot always be requested again immediately. Commands and retransmissions require days of schedule and light time. Some science data are sent in real time. Selected plasma wave data are stored on Voyager's digital tape recorder and played back later at a higher rate. The tape recorder belongs visibly to another technological era. So do the low data rates and the limited memory. Yet the signal crosses a distance no consumer network was designed to span. Performance has to be judged against the environment, not the calendar printed on the components. Voyager's transmission is also delayed history. The temperature reported today describes a machine almost a day earlier. Any failure visible in telemetry has already existed for hours before Earth knows it. The present state of Voyager is never directly available to its operators. The radio beam therefore carries both science and uncertainty. It says what happened. It cannot say what is happening at the instant the signal is received. At nearly one light day of distance, mission control always works with yesterday's spacecraft. On February 14, 1990, Voyager 1 performed an observation that did not serve the interstellar mission's fields and particles goals. Mission planners commanded the spacecraft to turn its cameras back toward the solar system and make a final family portrait. The sequence produced 60 images, including frames of 6 planets. Earth occupied less than a pixel. The spacecraft was about 3.7 billion miles from the Sun, beyond Neptune's orbit, looking inward toward bright solar glare. In the image that became known as the pale blue dot, scattered sunlight forms bands across the frame, and Earth appears inside one of them as a tiny point. The photograph does not show continents, oceans, weather systems, or the moon. It cannot distinguish a city from empty ocean. Nearly every human life then in progress occupied a dot with no visible surface. Scale removed all detail while preserving location. If you place yourself beside Voyager at that moment, the solar system is behind the camera's aim, but not arranged like a diagram. The planets occupy different directions and distances. The family portrait is a mosaic, not one ordinary wide-angle exposure in which every world lines up. The final result is an act of reconstruction. After the portrait, Voyager's cameras were turned off to save power and memory for the interstellar instruments. Their control software was later removed. The hardware remains attached, but the machine no longer looks outward in visible light. It travels through interstellar space without returning pictures of the view. That absence is scientifically sensible. Deep space near Voyager would appear mostly like a familiar star field. The local plasma and magnetic field cannot be photographed by an ordinary camera. Fields and particles instruments provide measurements that Earth-based telescopes cannot obtain from the spacecraft's location. The pale blue dot nevertheless changed the public meaning of the mission. Voyager had photographed Jupiter as a giant world, Io as an active moon, Saturn as a disk of thousands of ringlets, and Titan as a veiled globe. Its final image reduced the place of origin to almost nothing. Later in 2026, Voyager's distance from Earth will reach one light day from Earth. The pale blue dot image was taken at less than 1/4 of that present separation. The machine that made Earth a pixel has since added more than 12 billion miles to the gap. The portrait serves as a hinge. Before it, Voyager's defining record was visual: planets, rings, clouds, moons. After it, the record became increasingly invisible: solar wind speed, cosmic ray intensity, magnetic direction, plasma density, radio health. The last look home closed the camera era and gave the interstellar mission a bookend no later photograph could improve. The Voyager interstellar mission began formally on January 1st, 1990. Its science objectives shifted toward the termination shock, heliosheath, heliopause, and interstellar medium. These regions were predicted through models and indirect evidence, but their sizes and structures were uncertain. Without pictures, location had to be inferred through changing measurements. The solar wind is a plasma flowing outward from the sun, carrying magnetic field lines with it. Near the planets, the flow is supersonic relative to characteristic waves in the plasma. Farther out, pressure from the surrounding interstellar medium forces the wind to slow. The first major boundary is the termination shock, where the solar wind drops from supersonic to subsonic flow. Beyond it lies the heliosheath, a broad region of slowed, heated, compressed solar plasma. The heliopause forms the outer boundary of that plasma-dominated bubble. Outside lies interstellar material, though solar disturbances and magnetic influence can still reach across the boundary. Illustrations often draw these regions as smooth, nested shells. The real heliosphere changes with the solar cycle, interstellar pressure, direction, and time. Its shape may be asymmetric. A spacecraft samples one line through it, like a boat crossing one part of a large and shifting current. If you followed beside Voyager, no luminous membrane would announce a transition. Stars would not rearrange. The sun would remain behind. The evidence would appear in graphs. Particle populations dropping or rising, magnetic strength changing, plasma waves revealing a different density. This is why Voyager's surviving instruments matter beyond their age. A telescope near Earth can observe the sky but cannot directly sample plasma 15 billion miles away. Voyager occupies the environment. Particles pass through its detectors. Magnetic fields act at its sensors. The measurement is local. The interstellar mission also required a new relationship with time. Planetary flybys offered known dates. The outer boundaries could arrive within years or decades. Engineers prepared for a mission whose most important events did not have appointments. Instruments had to remain on, sequences had to repeat, and the team had to recognize a crossing after data revealed it. The first long milestone came not from plasma science, but from distance. Pioneer 10 had held the record as the farthest human-made object for decades. Voyager 1 was moving outward faster. Their paths pointed in different directions, and in 1998 the distances became equal. The machines never passed close to each other. One record changed hands across an enormous invisible arc. On February 17, 1998, Voyager 1 became the most distant human-made object from Earth and the Sun, overtaking Pioneer 10's distance at roughly 69.4 astronomical units. The word overtaking can suggest two vehicles on one road. Pioneer 10 and Voyager 1 were traveling in almost opposite directions from the Sun, only their radial distances crossed. Pioneer 10 had launched in 1972 and became the first spacecraft to pass through the asteroid belt and make a close encounter with Jupiter. Its gravity-assisted path carried it toward the constellation Taurus. Voyager 1 headed generally toward Ophiuchus, north of the ecliptic. A sphere centered on the Sun expanded past both trajectories, reaching Voyager first after 1998. If you could see the solar system from far above, the milestone would look like two thin rays extending from a common center. No physical baton moved between them. A calculation changed which point on the rays lay farther out. The record matters because it marks the edge of direct human reach. Telescopes observe across the universe, and radio signals travel much farther, but spacecraft are material objects carrying instruments, structures, and traces of Earth. Voyager 1 became the leading piece of that expanding material frontier. The distance at the 1998 crossing was about 6.5 billion miles. Radio signals then took roughly 9 hours and 36 minutes one way. Those numbers were already difficult to hold in ordinary experience. Voyager has since more than doubled the distance and the delay. Pioneer 10's science mission officially ended in 1997, and its final faint signal would be detected in 2003. Voyager remained active. The record, therefore, combined two qualities: farthest and still communicating. That second quality gives the distance scientific meaning. A silent object can mark a trajectory. A working spacecraft returns an environment. The outward speed remained about 1 million miles per day. Earth completed an orbit each year, sometimes moving slightly toward Voyager's direction and sometimes away. The distance counter could briefly run backward even while the spacecraft never reversed. Relative distance belongs to both moving endpoints. The sun's particle environment was changing more substantially. Voyager was approaching the region where the solar wind felt pressure from outside. Models disagreed about where the termination shock would occur. The boundary could move inward or outward with solar conditions. 6 years after taking the distance record, Voyager 1 encountered a lasting change near 94 astronomical units. The solar wind slowed. Energetic particles behave differently. The machine had reached the first major border in its interstellar mission. It did not cross out of the heliosphere. It entered the heliosphere's outer layer. Voyager 1 crossed the termination shock in December 2004 at about 94 astronomical units from the Sun. 1 astronomical unit is the Earth-Sun distance, nearly 93 million miles. 94 AU is roughly 8.7 billion miles, though exact Earth distance differs with orbital geometry. The termination shock forms because the solar wind cannot expand supersonically forever into the surrounding interstellar medium. Pressure builds. The flow slows below its local wave speed, compresses, and heats. The name shock describes a transition in plasma behavior, not an impact with a solid surface. On Earth, a supersonic aircraft produces a shock wave because disturbances cannot travel upstream through the approaching air fast enough to warn it. In the solar wind, characteristic plasma waves play an analogous role. Crossing the termination shock changes how information and pressure propagate through the flow. Voyager detected the region through particles, fields, and the changing solar wind environment. The exact crossing was not one permanent spherical radius. The shock can move inward or outward as solar conditions change, while the spacecraft's longer record established that it had entered the Heliosheath. If you crossed with the spacecraft, there would be no audible bang because ordinary sound cannot travel through near vacuum as it does through air. Instruments would register changes. Particle distributions would reorganize. Magnetic strength and turbulence would differ. The event becomes a boundary only after measurements are compared over time. The Heliosheath beyond was expected to be the final layer before interstellar space. Its thickness was uncertain. The spacecraft might need years to cross it. Power continued declining while the most desired boundary remained somewhere ahead. This created a race without a fixed finish line. The RTGs lost output predictably. Hardware aging did not. The heliopause location depended on conditions that models could estimate but not specify exactly. Voyager needed to remain healthy long enough for nature to reveal the answer. The plasma science instrument that would have measured bulk solar wind speed directly had stopped providing useful Voyager 1 data years earlier. Scientists therefore relied on other instruments and later on plasma wave oscillations. Missing capability did not make the mission blind, but it made interpretation more indirect. During the following years, Voyager sampled the Heliosheath. The outward solar wind speed eventually fell toward 0 in the radial direction. Cosmic rays from outside the heliosphere increased. Particles associated with the sun changed. Models were tested against a region no probe had entered before. The termination shock marked neither the end of sunlight nor the end of solar gravity. It was one physical change in the solar plasma. Voyager had crossed a border defined by speed and pressure. The larger border, defined by plasma origin, still waited ahead. The Heliosheath is often described as the region of slowed solar wind between the termination shock and heliopause. That sentence is correct, but too clean. Voyager found a changing environment filled with turbulence, energetic particles, magnetic structures, and pressure effects arriving from both the sun and interstellar space. The spacecraft spent almost 8 years there after the 2004 termination shock crossing. At roughly 1 million outward miles per day, 8 years represents nearly 3 billion miles of additional travel. A layer drawn as a narrow band in a diagram became a large fraction of Voyager's operational life. Scientists watched several indicators. Lower energy particles from inside the heliosphere could leak or escape. Galactic cosmic rays entering from outside could rise. Magnetic field strength and direction could change. None of these alone guaranteed that the heliopause had been crossed, because boundary regions can mix and fluctuate. You might picture two weather systems meeting, but the heliopause is not ordinary weather, and the densities are vastly lower than any terrestrial atmosphere. The useful resemblance is variability. Boundaries between flows ripple, shift, and transmit disturbances. A spacecraft's one-dimensional path records a sequence that scientists must translate into three-dimensional structure. In 2010, Voyager data showed that the outward velocity of the solar wind had fallen to 0 along the radial direction. The flow was being diverted, yet 0 outward speed did not automatically mean interstellar space. The spacecraft could still be inside a compressed region where solar plasma turned sideways. During 2012, particle counts began changing more dramatically. Galactic cosmic rays rose. Energetic particles associated with the heliosphere dropped, sometimes briefly and then durably. By August, some heliospheric particle levels fell by more than a factor of 1,000 compared with earlier years. One expectation created caution. Many models predicted that the magnetic field direction would rotate significantly when Voyager crossed from solar to interstellar plasma. The field strength increased, but its direction changed by less than 2 degrees. That observation seemed inconsistent with a simple crossing. Exploration becomes difficult when nature does not match the diagram. Scientists could declare the model wrong, declare the boundary uncrossed, or wait for another independent measurement. The Voyager team chose caution. A milestone this important needed stronger evidence. The date August 25, 2012, would later become the accepted crossing. At the time, mission scientists knew Voyager had entered a new particle environment. They did not yet have the decisive plasma density measurement. That evidence would arrive in an indirect way. A solar eruption sent a disturbance outward. More than a year later, the disturbance reached Voyager's region and made the local interstellar plasma oscillate. The spacecraft heard a density measurement in the pitch of a wave. Voyager 1's heliopause crossing is assigned to August 25, 2012. The date is reconstructed from abrupt and lasting changes in particle measurements, later supported by plasma wave evidence. The spacecraft was about 120 to 122 astronomical units from the Sun, around 11 billion miles away. Inside the heliosphere, the Sun's wind supplies much of the plasma. Outside, the local interstellar medium provides a denser population of charged and neutral material between stars. The heliopause marks the boundary where the solar wind no longer dominates the plasma environment. Crossing it made Voyager 1 the first human-made object to operate in interstellar space. The statement requires a definition. It does not mean the spacecraft escaped all solar influence. It does not mean it left the Sun's gravity or crossed the Oort cloud. It means Voyager passed beyond the plasma bubble inflated by the solar wind. If you had observed through a window, the crossing would have been invisible. The stars would retain their positions. The Sun would remain a bright point. There would be no line on the floor. The distinction existed in particles passing through detectors and in magnetic fields acting on sensors. The heliopause also proved less absolute than a wall. Solar eruptions continue to travel outward and disturb interstellar plasma. The magnetic field outside retained a direction unexpectedly close to the field inside. The region immediately beyond carried evidence of its proximity to the heliosphere. The accepted date emerged only in 2013. Science sometimes recognizes a boundary after the traveler has moved far beyond it. The spacecraft cannot pause at an ambiguous result while people debate. It keeps coasting, adding tens of millions of miles before the interpretation settles. The particle changes were compelling. Galactic cosmic rays rose to the highest levels of the mission. Lower energy particles associated with the heliosphere collapsed, but plasma density was the desired marker. Interstellar plasma near the heliopause was expected to be much denser than the outer solar wind. Voyager 1's direct plasma instrument was no longer useful. The plasma wave subsystem could still infer density if the plasma oscillated. Frequency depends on electron density. A higher characteristic pitch indicates more electrons per unit volume. For months, no suitable oscillation appeared. Then an outburst from the sun, launched in March 2012, crossed the same immense distance. In April 2013, it compressed the plasma around Voyager and made the electrons ring. The boundary had been crossed nearly 8 months before the measurement that proved it. On April 9, 2013, Voyager's plasma wave instrument detected local oscillations. The event was associated with a solar disturbance that had taken roughly 13 months to reach the spacecraft. As the disturbance passed, the surrounding electrons moved collectively and generated waves within the instrument's frequency range. The measurement could be translated into plasma density. The result was more than 40 times the density Voyager 2 had encountered in the Heliosheath. That was the kind of increase expected outside the heliopause in the local interstellar medium. Scientists then searched earlier data and found a fainter oscillation from October and November 2012. Extrapolating the measured density backward aligned the transition with the particle changes on August 25th. Several independent lines of evidence now supported one interpretation. You can listen to an audio conversion of the detected waves, but no microphone recorded sound traveling through air. The plasma wave antennas measured electrical oscillations. Researchers shifted or represented the frequencies so human hearing could perceive the pattern. Calling it the sound of interstellar space is poetic shorthand for a real electromagnetic measurement. If you hear the rising tone, the useful fact is not its mood. It is its pitch. Frequency becomes density. A wave becomes evidence that the spacecraft is surrounded by matter originating beyond the heliosphere. This method demonstrates how old instruments can answer questions not imagined in their original form. The plasma wave subsystem had studied radio emissions and plasma near planets. Decades later, it compensated indirectly for a failed plasma detector and supplied the decisive evidence for an interstellar crossing. The finding also corrected a model expectation. Magnetic direction had not rotated as sharply as predicted. Plasma density showed that Voyager was outside anyway. The boundary geometry and field connection were more complicated than the simplest pictures suggested. On September 12, 2013, NASA announced that Voyager 1 had been traveling in interstellar space for about a year. The machine was already hundreds of millions of miles beyond the accepted crossing point. News on Earth caught up with a spacecraft that never stopped. The measurement did not complete the mission. Interstellar space near the heliosphere is itself structured. Plasma density changes. Solar pressure fronts arrive after long delays. Magnetic fields fluctuate. Voyager became a permanent local probe moving through an environment sampled nowhere else along that line. Distance had turned a planetary spacecraft into a detector for the medium between stars. The same antennas that once listened near Jupiter now listen to plasma beyond the sun's wind. No image marked the transition. A faint oscillation did. Voyager 1 is in interstellar space, but saying it has left the solar system can mislead. The answer depends on which solar system is meant. The heliosphere is one domain. The sun's gravitational family is another. The solar wind bubble ends at the heliopause. The gravitational solar system may extend through the Oort cloud, a vast inferred reservoir of icy bodies. NASA estimates that Voyager could need about 300 years to reach the cloud's inner region, and perhaps 30,000 years to pass beyond its far side. This distinction places the 2012 crossing in scale. Voyager needed 35 years to reach interstellar plasma. It may need hundreds more merely to enter the Oort cloud, and tens of thousands to leave the broad region of objects still loosely governed by the sun. If you reduce the heliopause to the edge of a small plaza, the possible Oort cloud would extend across cities. The planets would be crowded near the center. Voyager's celebrated interstellar crossing would remain near the beginning of the larger gravitational map. The spacecraft is not headed toward a chosen star. Its current path points generally toward the constellation Ophiuchus, but constellations are directions, not nearby destinations. Stars move during the tens of thousands of years required for a close passage. Voyager's future encounter calculations account for that motion. The sun still affects the environment beyond the heliopause. Eruptions send shocks outward. Solar magnetic structures press on the boundary. Energetic particles can cross. Interstellar does not mean untouched by the sun. It means the ambient plasma comes from the space between stars rather than the solar wind. You can stand outside a shoreline and still feel waves from the landward storm. Boundaries separate dominant environments without erasing influence. Voyager samples that mixed neighborhood one measurement at a time. Language becomes part of accuracy. First spacecraft in interstellar space is supported by a physical definition and measurements. First spacecraft to leave the solar system hides the Oort cloud and the continuing gravitational domain. A calm account can hold both achievements without forcing one simple edge onto several different systems. The nested boundaries also deepen the title's distance. Voyager is far beyond every planet and beyond the solar wind bubble, yet it remains near the sun on the scale of neighboring stars. Its speed is high for a human machine and slow for interstellar travel. Its radio delay is nearly a day, while its nearest future stellar passage is tens of thousands of years away. The spacecraft occupies a middle distance with no ordinary human counterpart. Too far for quick conversation, too near for a star. Outside the heliosphere, inside the solar system's gravity. Still working. In July 2026, Voyager 1 remains more than 15 billion miles from Earth. NASA's live distance table is temporarily being refined for the coming milestone, but the broad map is clear. The spacecraft is the farthest human-made object, traveling outward at roughly 3.5 astronomical units per year. On November 18, 2026, the calculated Earth spacecraft separation will reach 16,094,799,096 miles. That is one light day from Earth. The precise time matters because both endpoints move. Earth races around the sun at about 18.5 miles per second. Voyager follows a different path at about 17 kilometers per second relative to the sun. The line between them stretches and shortens slightly through Earth's orbit. The milestone is therefore a relationship, not a fixed shell surrounding the sun. Voyager can be one light day from Earth while a somewhat different distance from the Sun. Months later, Earth may move along its orbit and the separation can change in a non-uniform way, even though Voyager keeps escaping. If you send a command at the milestone, it arrives roughly 24 hours later. If the spacecraft responds immediately, confirmation returns another 24 hours after that. A simple exchange occupies almost 2 days. Diagnosis requires more than one exchange. A cautious repair can unfold across weeks. The current position is also far above the planetary plane. Voyager's 35-degree northward path means an overhead map can hide much of the geometry. A side view reveals the climb. The spacecraft is not following Pluto outward along the ecliptic. It is moving away from the disk that contained every planetary encounter. Nothing nearby provides a visual landmark. Interstellar gas contains particles, but their average separation makes the environment an excellent vacuum by terrestrial standards. The closest large object remains the Sun, though it is no longer visually large. The nearest stars are still light years away. Voyager itself remains physically ordinary in size. The dish is still 3.7 meters across. The central bus is still about 1.8 meters wide. Distance has not enlarged the machine. It has enlarged the sphere across which people must infer its condition. Every telemetry frame closes that sphere for a moment. A voltage measured aboard Voyager becomes a pattern at Earth. A magnetic direction sampled in interstellar space becomes a number on a screen at JPL. The most distant working artifact enters a room through radio. The map in 2026 therefore contains two opposing facts. Voyager is almost a full light day away, farther than any machine has operated, and it remains connected closely enough for engineers to change which instrument draws power, relocate computer code, and revive thrusters considered unusable for 20 years. Distance has slowed the conversation. It has not ended it. As of April 17, 2026, Voyager 1 has two operating science instruments, the magnetometer and the plasma wave subsystem. 10 investigations once supported the planetary mission, with an additional radio science investigation. The active pair now measures an environment that cannot be sampled from anywhere near Earth. The magnetometer uses sensors on the long boom to measure magnetic field strength and direction. In interstellar space, those readings help trace the local galactic field and the continuing influence of the nearby heliosphere. Pressure fronts, solar disturbances, and regional changes appear as variations over time. The plasma wave subsystem uses the two long V-shaped antennas. It covers frequencies from about 10 Hz to 56 kHz. Plasma oscillations reveal electron density. The same instrument that helped confirm the 2012 heliopause crossing can continue following density farther into the local interstellar medium. These instruments do not return the kind of data that produces a new planetary portrait. Their records are lines, spectra, counts, and time series. The scientific value lies in continuity and location. No other active spacecraft occupies Voyager 1 foot's path outside the heliosphere. Continuity allows a disturbance to be followed long after its origin. A solar eruption observed near Earth can propagate through the heliosphere for months, cross the heliopause, and compress plasma near Voyager. Researchers compare the timing of the event with magnetic changes and plasma wave frequencies. The spacecraft becomes a remote station in a system-wide experiment whose other stations may include satellites near Earth and Voyager 2 on another trajectory. Distance also separates local variation from broad structure. One isolated reading cannot reveal whether density is rising steadily or whether the spacecraft has crossed a temporary compression. Years of measurements can show trends, repeated shocks, quiet intervals, and gradients. The value of the remaining instruments therefore grows from patience. Their modest data rates accumulate a record no short-lived probe could substitute. If you could move the magnetometer back to Earth, it would no longer answer the same question. environment is not carried with the instrument. Voyager's uniqueness comes from placing modest sensors where no replacement can soon arrive. The cosmic ray subsystem operated until February 25, 2025. It had measured high-energy particles from solar and galactic sources through the planetary mission, Heliosheath, and boundary crossing. Turning it off saved power. The low-energy charged particle experiment continued until April 17, 2026, nearly 49 years after launch. The LECP instrument included a small motor that rotated a sensor platform to scan different directions. NASA kept that half-watt motor running after the experiment was switched off, preserving a possibility that the instrument might someday be reactivated if power could be found. Half a watt is small, but the decision shows the precision of the mission's remaining margins. Instrument shutdowns also change interpretation. Earlier heliopause science relied on several particle detectors, plus magnetic and plasma wave observations. Future measurements come from a narrower set. Researchers compare the new record with decades already archived and with Voyager 2's different path. Two instruments are not a symbolic remnant. They are an active observatory matched to the final mission. One measures magnetic structure. One measures plasma waves and density. Together they read the medium between stars in ways the cameras never could. The machine has become simpler as its location has become more unusual. Each remaining watt supports fewer measurements, but every measurement comes from farther out. Voyager's long life is often described as durability. Durability alone is incomplete. The spacecraft has survived because engineers repeatedly reduced what it does. Capability has been exchanged for operational time in a planned sequence. The cameras went off in 1990. The photopolarimeter had failed much earlier. Infrared, ultraviolet, planetary radio, plasma, cosmic ray, and low-energy particle systems ended at different dates for different reasons. Some instruments degraded. Others remained usable, but cost power the mission could no longer spare. The RTGs lose about 4 watts of electrical output each year. That decline is gradual enough to plan around and relentless enough to require action. Waiting until demand exceeded supply could trigger the undervoltage protection system and switch off components automatically. Engineers prefer to choose deliberately before the spacecraft chooses for itself. In February 2026, during a planned roll maneuver, Voyager 1's power level fell unexpectedly. NASA reported that any additional drop might have triggered undervoltage protection. The team decided that the LECP experiment would be next in the established shutdown order. Command sent in April retired it. Because the spacecraft was more than 15 billion miles away, the command sequence needed about 23 hours to arrive. The shutdown itself was planned to take about 3 hours and 15 minutes. Confirmation then crossed the same distance home. Turning off one switch became a 2-day operation surrounded by analysis. If you manage power in a room, you can see the lights change immediately. At Voyager, operators predict electrical, thermal, and software consequences before receiving proof. They must consider whether a cold instrument could ever restart, whether a heater can remain off, and whether an autonomous response might interpret the new state incorrectly. The loss of an instrument can extend the life of the bus, radio, and remaining science. NASA estimated that shutting down LECP would provide roughly a year of breathing room while engineers pursued broader savings. The exact future remains conditional on hardware health and power behavior. Subtraction also occurs in heating. Components designed for certain minimum temperatures have operated below them after heaters were turned off. Some margins proved larger than tests had established. That success does not make the risk disappear. It gives mission managers another carefully observed option. The spacecraft of 2026 is therefore not the spacecraft of 1977, running unchanged. It is the same physical artifact in a radically reduced configuration. Dark instruments remain attached. Their cables, structures, and histories travel onward, while electricity is concentrated on communication, control, thermal survival, and two sensors. Longevity is visible in what remains. It is equally visible in what the team was willing to release. On November 14th, 2023, Voyager 1 stopped sending readable science and engineering data. Ground controllers could tell that it was still receiving commands and otherwise operating, but the returning stream no longer contained usable information. The machine was speaking in a pattern Earth could not interpret. The problem was traced to the flight data subsystem, which packages measurements and spacecraft status for transmission. A single memory chip had failed. Part of the software code stored on that chip was lost, and the missing instructions corrupted the output. There was no way to replace the component. Engineers instead studied the remaining memory and chose to relocate the affected code. No one open area was large enough to contain it. The team divided the code into sections and placed those sections in separate locations, then adjusted references elsewhere so the pieces could continue functioning as one logical program. If you tear one page from a tightly packed manual, copying the page elsewhere seems simple. The Voyager problem was closer to cutting the missing page into paragraphs, placing each paragraph in a different margin, and revising every instruction that referred to the old page number. All changes had to fit without damaging existing content. The first relocated section handled engineering data. On April 18, 2024, JPL transmitted the change. At the time, the one-way light time was about 22.5 hours. Engineers waited through the outbound day and the return day. On April 20th, readable information about Voyager's health appeared again. If you had been in the control room, the decisive moment would not have involved seeing the spacecraft move. A formatted stream would begin making sense. Temperatures, voltages, and states would occupy their expected places. Coherence itself would be evidence of repair. The team then relocated and adjusted other affected code. On May 19th, they commanded the science return. 2 instruments resumed normal operation immediately. 2 required additional work. By June 13th, all 4 instruments active at that time were returning usable science data. The repair demonstrates why documentation and preserved expertise matter. Voyager's computers were already old when many current engineers began their careers. Ground tools and institutional knowledge change. Solving the failure required understanding a memory architecture created before modern personal computers became common. The success was not permanent immunity. Cosmic radiation, thermal stress, and age continue. The repaired code occupies a new map with less flexibility. But the mission recovered from a failure that had made its most important output unreadable for 5 months. Across more than 15 billion miles, people changed where a 1977 computer stored its thoughts. Communication depends on pointing, and pointing depends on hydrazine thrusters. Voyager fires very small pulses to keep its high-gain antenna aligned with Earth. After decades, the fuel itself is not the only concern. Tubes carrying it have been narrowing. NASA identified the buildup as silicon dioxide, a material produced over time from a rubber diaphragm in the fuel tank. The residue accumulates inside fine inlet tubes. As openings constrict, thrusters become less efficient and must fire more often to create the same control. Voyager carries several thruster branches. Primary attitude thrusters control pitch and yaw. Roll thrusters rotate the spacecraft around the antenna axis to keep a star tracker aligned. Trajectory correction thrusters, once used during planetary flight, were revived decades later as substitutes when other branches degraded. In 2024, engineers switched Voyager 1 to a different set of thrusters after balancing power and temperature risks. One necessary heater could not simply be activated while every science instrument remained on. Temporary changes had to be planned so the propellant path warmed enough for safe operation. An even older problem involved primary roll thrusters considered unusable since 2004. Two internal heaters had lost power, so the mission relied on a backup set for 20 years. By 2025, those backup lines were themselves approaching concerning levels of clogging. The team revisited the old failure and developed a new hypothesis. A change in the heater control circuit might have left a switch in the wrong state, rather than leaving the heaters physically destroyed. If commands restored that state, the long-dormant thrusters might warm and work again. The attempt carried risk. Cold propellant reaching a firing thruster could create dangerous behavior. The star tracker had to be aligned precisely so an automatic roll correction would not occur before the heaters were known to work. Light time meant the team would learn the result almost a day after the spacecraft experienced it. On March 20th, 2025, telemetry showed the heater temperature rising. The primary roll thrusters had returned. Hardware declared dead in 2004 became an operational backup in 2025 without anyone touching the spacecraft. If you hold a clogged tube in a workshop, you can examine, clean, or replace it. Voyager permits none of those actions. Engineers can switch paths, adjust temperatures, reduce firing frequency, and reinterpret old circuitry. Maintenance becomes choreography among parts already on board. The achievement did not remove aging. It created options. One branch can rest while another works. A backup can be preserved. The antenna can remain pointed longer. Voyager's survival repeatedly depends on this form of ingenuity. Not adding new hardware, but finding an unused possibility inside the hardware that left Earth nearly 50 years earlier. We have talked about a rocket lifting from Florida on September 5th, 1977, carrying a spacecraft designed for 5 years into a mission that would approach 50. We have talked about more than 10,000 possible trajectories and an outer planet geometry that opens roughly once in 175 years, turning positions of moving worlds into a narrow path through time. We have talked about Jupiter bending that path, about Io's volcanic plume rising above a moon that was not geologically dead, about Europa's crossed ice, and about a faint ring revealed beside the largest planet. We have talked about Saturn's thousands of ringlets, waves moving through orbiting ice, small moons keeping edges sharp, and Titan hiding its surface beneath a nitrogen-rich orange atmosphere. We have talked about the Titan bargain, the close encounter that delivered knowledge of the moon while bending Voyager northward away from Uranus, Neptune, and every later planetary destination. We have talked about 3 warm ARTIJ converting plutonium decay into a declining electrical supply, and about 4 watts disappearing each year from a budget already measured in hundreds rather than thousands. We have talked about computers executing only thousands of instructions per second, a dish 3, 7 meters wide, commands moving at 16 bits per second, and a 23-watt radio crossing a darkness that now consumes almost a day of light. We have talked about a camera turning home in 1990, reducing Earth to nearly 1 pixel from 3. 7 billion miles, then going dark while the spacecraft continued outward without another photograph. We have talked about Voyager passing Pioneer 10 without coming near it, crossing a mathematical distance record along a different ray from the Sun. We have talked about the termination shock at roughly 94 astronomical units, years within the Heliosheath, particle counts changing in 2012, and a magnetic direction that refused to match the cleanest prediction. We have talked about interstellar plasma ringing after a solar disturbance, its pitch revealing a density more than 40 times that of the Heliosheath and confirming a boundary crossed months before. We have talked about a failed memory chip, code divided across surviving spaces, thruster lines narrowed by residue, heaters restored after 20 years, and instruments surrendered one by one so two could remain. This is the journey mile by mile, but the miles do not all mean the same thing. The first miles were paid for by rocket propellant. Millions more were shaped by planetary gravity, billions accumulated through coasting. The final miles of the active mission are measured not only by position, but by the survival of a radio link. Voyager has traveled outward continuously while its purpose changed. Planetary scout, photographer, distance record holder, heliopause probe, interstellar observatory, engineering patient, each identity remains attached to the same bus and dish. The machine has become less capable and more singular. It can do fewer things than in 1979. It does those things in a place no other working spacecraft has reached. Bolted to Voyager 1 is a 12-inch copper phonograph record plated with gold. An aluminum cover protects it. Symbolic diagrams describe how to play it, where the spacecraft came from, and how to interpret its timing. A small sample of uranium-238 provides a radioactive clock with a half-life of about 4.468 billion years. The record contains 115 images encoded in analog form, natural sounds, music from different cultures and eras, spoken greetings in 55 languages, and messages representing Earth in 1977. It is not a complete portrait of humanity. No object that small could be. It is a deliberate sample assembled by a committee led by Carl Sagan. The images are not printed photographs on the gold surface. They are encoded as signals that can be reconstructed line by line. The cover diagrams use the transition of neutral hydrogen as a proposed universal clock, a map of pulsars to indicate the sun's location, and a drawing of the record in stylus. The uranium sample offers another measure of elapsed time through decay. Each instruction assumes that a finder can infer physical relationships from symbols without sharing a human language. Those assumptions may never be tested. They are still revealing. The designers tried to separate local convention from reproducible physics, wavelength instead of inches, pulsar periods instead of place names, decay instead of a printed year. The cover is an exercise in communicating when no shared culture can be presumed. The contents then reverse the approach, offering particular voices, music, bodies, landscapes, and living things from one world at one moment. NASA describes the record as a time capsule and notes that it would be played only if an advanced spacefaring civilization encountered the spacecraft. The chance is not estimated as high. Interstellar space is immense, stars are small targets, and Voyager is not aimed at an inhabited world. The next relatively close stellar passage illustrates the scale. In the year 40,272, Voyager 1 is calculated to pass within about 1.7 light-years of a star, designated AC plus 79,3888. 1.7 light-years is more than 100,000 astronomical units. Close-in stellar navigation remains far beyond the distances of planetary flybys. Before then, Voyager may spend roughly 300 years reaching the mottled inner Oort cloud, and perhaps 30,000 years crossing the broader cloud. The radio will be silent long before either event. Available power will fall below what communication and control require. The last telemetry will arrive on an ordinary day after a delay of many hours. If you imagine that final signal, it may not announce a dramatic failure. A carrier may weaken beyond recovery. Pointing may drift. A transmitter may lose power. The transition from active spacecraft to silent artifact could be known only as the absence of another frame. Motion will continue. No engine must remain on. Voyager will coast around the galaxy under the combined gravity of the Sun, stars, molecular clouds, and the Milky Way. Its exact path will evolve over immense time. Dust impacts and radiation will alter surfaces. The golden record's cover is intended to protect what it can. The record gives the silent future a human object. Long after the magnetometer stops measuring, the artifact will still carry surf, wind, thunder, animals, music, voices, diagrams, and photographs. It carries instructions for an encounter almost certain never to happen. That does not make the gesture empty. The record was also made for the people who sent it. It states that a machine leaving the planets should carry evidence of more than machines. Voyager's radio describes where humanity can reach. The record describes, selectively and imperfectly, what kind of world did the reaching. The loneliest machine carries company in grooves. The honest answer to the title is that Voyager 1 is not lonely in any measurable scientific sense. Loneliness belongs to minds, and Voyager has no mind. It does not feel the cold, count the years, recognize the golden record, or wait emotionally for Earth to answer. But as a human description, the title fits. Voyager is the farthest artifact still in conversation with its makers. It has no destination scheduled, no companion flying nearby, no camera still looking, and no repair crew that can follow. Its next stellar passage is tens of thousands of years away. The nearest meaningful relationship in its operation is a radio link stretched across more than 15 billion miles. That relationship keeps the story from becoming one of abandonment. Engineers still schedule antennas, read yesterday's telemetry, calculate temperatures, revise memory maps, and decide which half-watt motor should remain on. Scientists still receive magnetic directions and plasma waves from beyond the heliopause. The spacecraft's solitude is physical. Its mission is collaborative. The phrase mile by mile also changes at the end. No one tracked each individual mile as a separate event. The useful milestones were launch, gravity assists, planetary encounters, a photograph, a distance record, a shock, a plasma boundary, and a sequence of repairs. Between them lay billions of nearly indistinguishable miles crossed by momentum. If you compress the entire route into one day, the planetary encounters occupy the first few minutes. The pale blue dot arrives early. The heliopause appears late in the afternoon. The present spacecraft approaches midnight, still moving with almost the same outward speed it carried decades before. On November 18, 2026, Voyager will become the first human-made object one light day from Earth. A signal sent from Earth that morning reaches the spacecraft the next morning. An immediate answer reaches home another morning later. 2 dawns can pass during one exchange. The distance does not make Voyager close to another star. One light day is only about 1/365th of a light year. Proxima Centauri is more than 4 light years from the Sun. Interstellar travel remains a domain in which the fastest distant probe has barely begun. Yet barely begun is not the same as nothing. A machine built with 65,000 parts crossed Jupiter's radiation, Saturn's ring plane, billions of miles of solar wind, the termination shock, the Heliosheath, and the heliopause. It recovered from failed memory and revived old thrusters. It reduced itself from a planetary observatory to 2 instruments and a voice. The voice is faint. The message is small. The achievement is in continuity. Voyager does not need to arrive anywhere else for the mission to have meaning. It has already turned the solar system from a telescopic arrangement into visited worlds. It has already measured the border between solar and interstellar plasma. It has already looked back and placed Earth inside a single point of light. Now it carries that point outward. A dish facing home. 2 instruments awake. 3 warm generators fading. A golden record waiting for no promised listener. 1 light day from Earth. Still moving. Still returning a signal. Good night.